In this video, we are going to look at how to solve a type of first-order differential equation called a separable differential equation. So the idea with a separable differential equation is you can essentially separate the terms with y from the terms with x. So imagine that you have a first-order equation, and perhaps after rearranging terms, you can put it in this form, where we have dy dx, here y is a function of x, equals whatever else is over on the right-hand side, but the idea is that we could separate this into the product of terms with x and terms with y. So here, to denote that, I have f of x times g of y. Typically, you'll be looking at actual expressions here. We'll see examples. If your differential equation can be written in this way, then we can use the technique of separation of variables to try to find the solution to this differential equation. What I'm going to do is separate x and y. So I'm going to put everything with y, say, on the left-hand side. I'm going to divide over by g of y to write 1 over g of y, and leave the dy on the left-hand side, so that everything to do with y on the left-hand side turns into 1 over g of y times dy equals, put everything with x over on the right-hand side. That's going to be this f of x expression together with dx. Okay, this is a strange thing to write down because the expression dy dx is not a fraction. It's not numerator dy, denominator dx, like the number 3/4 or something like that. It's a rate of change. However, this is a technique. It's giving us a way to try to find the solution y as a function of x. So what we now do after rearranging our equation so that we've got y on one side and x on the other is we integrate. So we'll integrate this left-hand side. That's going to be an integral with respect to y, and integrate this right-hand side. So here we'll be anti-differentiating with respect to y. Here we'll be anti-differentiating with respect to x. And then we want to solve for y when we can. So if I can then isolate y, we'll find an explicit solution to this differential equation. This technique is called separation of variables. So what I would like to do next is several examples, or I think maybe 4 examples. So I'll give you 4 differential equations, which may or may not also have initial conditions. We will separate the variables, we'll anti-differentiate. There are certain expressions that you tend to see if you do separation of variables over and over. So we'll see some of those emerge in our examples. And then I will wrap up this video with just a brief justification of why this technique is a good idea. So this separating here is a little bit strange because I broke apart the expression dy dx, but I will essentially use the chain rule to justify that, yes, this is what we want to do in this situation. Okay, let's start with this example. We would like to solve the differential equation dy dx equals x times y. So literally the right-hand side is x times y. So it's a function of x times a function of y. Let's separate these. So what I'm going to do is divide over by y, essentially multiply over by dx. So I'll write 1 over y dy equals x dx. I personally do not like this kind of expression without also the integration kind of brought into it. So I immediately then write the integral symbol in front. To me, that just looks a lot nicer to have the dy and dx in the context of integration. Now we are going to integrate both sides, the left-hand side with respect to y, the right-hand side with respect to x. Both of these integrals are indefinite. So what I'm going to do just for this one and only time is I'm going to pick up a constant of integration when I do both integrals, but then we will realize that we really only ever need one constant of integration when we do the separation of variables. Okay, so what's the antiderivative of 1 over y? It's natural log of the absolute value of y. Plus, throughout today's video, what we're going to have are lots of constants of integration, and we're going to do algebra on those constants of integration. So I'm going to use subscripts to distinguish between the constants. I'll talk a little bit more about that at the end, but let me just say C1, meaning the end of this problem and as we work through examples. C1 is the constant I'm picking up right now when I integrate 1 over y with respect to y. On the other hand, when I take the antiderivative of x with respect to x, it's x squared over 2 plus another constant. And just to say, hey, that's another constant, I'm going to denote that with C subscript 2. Okay, but here's the thing, is constant on the left, constant on the right. I would then subtract C1 over from C2. C2 minus C1 is just another constant. So there's no need to have two constants here because we can just merge them into one on the right-hand side. So what I typically would do, and what I will do in all future examples, is not pick up a constant on the left-hand side. So normally from here to here, I would write natural log of the absolute value of y equals x squared over 2 plus a constant of integration. This would normally be my first step after writing down the separation of variables. Because I've got yet another constant, it's technically C2 minus C1, I'm going to write C3, where the idea here is C3 is C2 minus C1. And again, I'm going to address this issue with constants at the end of this problem. Okay, we now would like to solve for y whenever we can, and we can do that in this example. So I've got natural log of the absolute value of y equals x squared over 2 plus a constant. In order to isolate at least the absolute value of y, we need to exponentiate both sides. So I'm going to raise e to the left-hand side and set that equal to e to the right-hand side. So on the left-hand side, we will have e to the natural log of the absolute value of y. And on the right-hand side, we'll have e to the x squared over 2 plus c3. And let me keep going to the right. By laws of exponents, e to something plus something is the product of e to the first term times e to the second term. That means that this expression can be rewritten as e to the x squared over 2 times e to the c3, like that. Okay, let me pause here and just let you digest what's happened. See what you want to do on the next line. So go ahead and write the next line, then I will come back. Okay, here's where we're going with this exponentiation. E and natural log are inverse functions. So on the left-hand side, e to the natural log of absolute value of y is just going to leave us with the absolute value of y. On the right-hand side, there's nothing we want to do to e to the x squared over 2. That's just what it is. E to the c3 is just another number. So c3 is a number. E raised to that is a number. So this is just another number. Let's give that number a name, and I'm going to call it C4. So we'll call this C4. So we'll say the right-hand side is C4 e to the x squared divided by 2. Okay, so that is now looking better than where we started. We have the absolute value of y on the left-hand side, and I want to solve for just y. This is not an unusual thing to see whenever you're doing separation of variables. Sometimes you have 1 over y like this or something similar, and you end up with this absolute value of y expression. In fact, we're going to see it again in this very video. So what I want to do is work through in detail what's going to happen, how to address this absolute value, and in the future, we'll be a little bit more casual with it. Okay, so let's consider maybe 3 different possibilities. What if y is, let's say, 0? So let's start with 0. Okay, so we've got 3 different situations for y to think of. Okay, so what if y, our function that we're trying to look for, is ever equal to 0? Well, in that case, the absolute value of y is y. But more importantly, if I look back at my differential equation, if y is ever 0, then the derivative of y with respect to x is also 0. We are at what we think of as an equilibrium solution. Y will stay 0 forever. So regardless of x, if y is ever 0, it stays 0 forever. So this would be the solution were that the case. It would just be y equals 0. We could think of that as y equals 0 times e to the x squared over 2. It's a bit of a silly thing to write down without this context, but there's a reason why I want to do that. Is I want to have the most general representative form for solutions to this differential equation that I can, and this is going to fit into that form. Okay, so if y equals 0, it stays 0 forever. So what if y is, say, on one side of 0? What if y is positive? I just realized I wanted to make a little note here. Let me add this, that C4 is e to the C3. Okay, just trying to keep track of my constants. Okay, got off topic there for a second, but let's go back to the question, which is what if y is greater than 0? If a solution y is ever positive, then based on our conclusion from the first case, we actually know that it's going to be positive forever. So when I look at this solution down here and I have the absolute value of y, we can say, hey, you know what? This function is always positive, and the absolute value of y is just plain old y. So writing absolute value is superfluous. That would mean that the solution to this differential equation, we've already found, it's just plain old y equals this constant times e to the x squared over 2. Like that. Now let's address the third possibility, which is what if y is negative? Again, based on this equilibrium solution at 0, if y is ever negative, it's going to stay negative forever. So if I look at the situation where y is negative, then we know that the absolute value of y needs to flip the sign of y. We do that by throwing a negative in front of y. So if y is negative, the absolute value of y is -1 times y. That makes it positive because y is negative. So now if I come to this left-hand side and replace it with -y, we would say -y equals this constant C4 e to the x squared over 2. So now if I want to solve for y, I'm just going to multiply both sides by -1 to get y equals -C4 e to the x squared over 2, which if you want to, you could take this -C4 and replace that with a new constant, because that's just another number, about C5 e to the x squared over 2. Okay, let me step back for a second, and then I will summarize these three cases, and we'll just have one form of the solution. In all three situations, we were able to put the solution y into the same general expression. Y is a constant times e to the x squared over 2, so here that constant is 0. Y is a constant e to the x squared over 2, where here the constant is positive because we know it's e to a number, and that's always a positive expression. So here y is a positive constant times e to the x squared over 2. In this third situation, y is negative that, so y is a negative constant, e to the x squared over 2, but in all three situations, y was a constant times e to the x squared over 2. So the general form of the solution is going to summarize all three in just one line. We'll say the solution is y is a constant times e to the x squared over 2. This is the form of the solution to this differential equation. Let me make this a little better. Here, C could be 0, it could be positive, it could be negative. It covers all three cases. So we'll just say C is any real number. Okay, so that is our solution to this differential equation. And again, if y is 0, that just means we choose that leading constant to be 0. If y is going to be a positive solution, like in case 2, this leading constant will be positive. If y is going to be less than 0, this leading constant will be negative. So what I do is when I get to this part right here, and I've got the absolute value of y is this constant times this exponential function, I would say, you know what? Let me just drop the absolute values and let the constant absorb the sign of y. So I typically do not go through this whole argument right here if I recognize that positive, 0, negative scenarios for y could be absorbed by this leading constant as we have in this example. We will see this again when we do the exponential growth equation later. I think it's the third example. So let's go ahead and set this aside for now, and we will do another example of separating variables. This second example is an example of an initial value problem. So we would like to solve the separable differential equation dy dx equals 3x squared y squared with an initial condition that when x is 1, y is 4. So often initial conditions are when x is, say, 0. Here it's 1. Not that big of a deal. We will plug in x equals 1 and y equals 4 into the general form of our solution when we've gotten that. So the first thing we need to do is just solve for the general form. So let's go ahead and separate this into terms with y and terms with x. I recommend leaving constants on the right-hand side with x. It's just usually easier that way. So I'm going to say 1 over y squared dy equals 3x squared dx. And you'll notice that as I wrote that, I went ahead and dropped in the integral symbols just because I like to see that all at the same time. So we've got y squared on the left, 3x squared on the right, dy on the left, dx on the right. Anti-differentiate now for the left-hand side. The antiderivative of 1 over y squared is negative 1 over y. This time I'm not going to bother with the constant of integration on the left-hand side because it will just absorb everything into the right-hand side. The antiderivative on the right is x cubed plus our first constant. So I'm going to write c1. And any modifications we make to that, we'll just rename that constant by changing the subscript. Okay, let's now isolate y. So multiply both sides by negative 1, and we'll have 1 over y equals negative x cubed minus c1, which isn't too bad. But I'm just doing algebra on c1. To get into the theme of editing constants, I'm going to write plus c2. This is optional. It's just the choice I'm making here to replace c1 with a negative c1 with a new constant called c2. Still trying to isolate y, so let's take the reciprocal of both sides of this equation. On the left-hand side, we'll have y. And on the right-hand side, we'll have 1 over negative x cubed plus c2. At this point, we've solved for y, so we've got the general form of the solution. Y equals 1 over negative x cubed plus c2. This solution isn't necessarily going to exist for all values of x. In particular, if the denominator is ever 0, this wouldn't be a solution to this differential equation. But let's not get too off topic here. I just want to show you the method of separating variables and finding the general form of the solution that way. Okay, so given this, I would like to actually solve an initial value problem. So what happens when x is 1? Y should be 4. So for the initial value problem, y is 4 when x is 1. So 4 equals 1 over negative 1 plus c2. What I'd like to do here is solve for c2. That's the goal. So maybe take the reciprocal again. So 1/4 equals c2 minus 1. I'll write it that way. This tells me that c2 is 1 plus a fourth, so 5/4. Okay, so now I've got that constant. We can go back to this form of the solution and replace this constant now with what we just found. So y equals 1 over, I'm actually going to switch the order here. I just think it looks a little prettier that way. So 5/4 minus x cubed. And then again, just to make it look better, I'm going to multiply this fraction by 4 over 4 to write that the solution is 4 divided by 5 minus 4x cubed. Okay. Let's check that this does indeed solve this differential equation. So I'm going to step aside for a second and let you finish writing this down, then I'm going to erase everything. We can go ahead and verify that when x is 1, y is 4 divided by 5 minus 4, so 4 over 1 is 4. It satisfies the initial condition, but what I'd like to just revisit for a minute is the idea that this solves the given differential equation. So let me step away, and then I will clear the board, and we will check that we really have solved our differential equation. Okay, let's check our work. That's one nice thing about solving differential equations like separable differential equations is at the end, you can see if you've done the right thing. So you can check, does this function, y equals 4 divided by 5 minus 4x cubed, solve the given differential equation? We've already verified that when x is 1, y is 4. So the right-hand side of the question that we were given is satisfied. But does this also satisfy that dy dx is 3x squared y squared? So let's differentiate both sides with respect to x. That's going to give us the left-hand side that we want to see, dy dx. And on the right-hand side, if I think of this like quotient rule, low d high is 0, minus high d low is -4, d low is going to be -12x squared like that, all over low low. So the quantity 5 minus 4x cubed is going to get squared. Typically with the quotient rule, you don't want to square out the denominator, and we don't want to do that here. One nice thing about checking your work is that you're allowed to know what you're hoping to land on. So I would like to see 3x squared y squared. So I keep that in mind as I simplify. This is 48. So -4 times -12 is 48, but I know I'd like to have a 3 in there. So what is 48 divided by 3? That's 16. Let me write 48 as 3 times 4 squared times x squared. So normally I wouldn't take the number 48 and write it that way, but I know that I'm looking to have that leading 3. I also think that things are going to get squared. Okay, so 3, 4 squared, x squared, all over the same denominator as before, 5 minus 4x cubed squared. And now we've got 3x squared, and then this looks a lot like y. In fact, let me write it down here. So we'll have 3x squared. I'm going to peel those expressions from the numerator out front. And then 4 squared over this denominator squared, I'm going to write that as the single fraction 4 over 5 minus 4x cubed, all that squared. But then this expression in here that I'm squaring is literally y, so it's up here. So we've got y back, so that this is now 3x squared y squared. And that's exactly what we wanted to see. Okay. That's one thing I wanted to do. The other is I wanted to revisit an issue that I brought up and then set aside while I was solving the original problem. And that is that the solution we have here is not going to be valid for every value of x because we have a denominator which might be 0. So let me just mention that we do not want, or we cannot have 5 minus 4x cubed equal to 0. So that means that we don't want to see 5/4 equal to x cubed, or in other words, x cannot be the cube root of 5/4. Okay. Given that we were told that at some point for our function x was 1, that means that the solution we're looking at is going to live to the left of this number. So our solution is not valid for all values of x. Let's say we're going to take this solution to work for x values less than the cube root of 5/4. Let me actually step aside now and let you see the slope field for this differential equation. I'm going to add the solution to it. So you will see a curve for all x values to the left of the cube root of 5/4. Okay, for this third example, our differential equation is dy dx equals 4x cubed divided by y minus sine of y. So let's put all the things with y on the left-hand side. It's going to be y minus sine of y dy. Everything with x on the right-hand side, that's going to be 4x cubed dx. And then in the usual way, I'm going to immediately write that we are doing integration. Okay. All right, let's anti-differentiate. The left-hand side, we will have y squared over 2 plus cosine of y. On the right-hand side, just x to the fourth plus our first constant. First time we see that constant. And you know what? This is all that we're going to do because we cannot isolate y in this equation. I've got y squared, I've got cosine of y. I cannot find an explicit solution y equals stuff with x on the right-hand side. So there's no explicit way to solve for y here. This is going to be an implicit solution. Let me put up, for random choice of this constant here, a picture of all of the points in the xy plane that satisfy this equation. So the thing is that what is the graph of an equation? It's a way of visualizing all of the points that make an equation true. So here's a snapshot of what that would look like. Now, this is not even a function. Y is not a function of x, and x is not a function of y. However, what we can say is that if you were to pick any point on the graph of this equation, and you were to use, say, implicit differentiation to find the slope of the line tangent to the graph of this equation at that point, so here we go, like here's an example, then the slope satisfies that dy dx equals 4x cubed divided by y minus sine of y. So this is like a relationship between x and y that makes this differential equation true. Okay, let's use separation of variables to revisit a famous differential equation that we've looked at before. This is the exponential growth model. Here I've written it as dp dt equals some parameter k times p, where we can think of p as like a population over time, so p depends on the independent variable t. We've already looked at this equation, but I just want to show how it can be viewed as a separable differential equation. There's actually no t on the right-hand side, but that's okay. We could think of this as a function of p times the number 1. Or what I'm actually going to do is leave k on the right-hand side. So let me put p on the left-hand side and write 1 over p dp, and then k dt. So that's how I'm going to separate it so that we've got everything with p on the left, everything with t on the right. There's not a lot with t, but we have separated this. Let's do some anti-differentiation. On the left-hand side, we're going to have the natural log of the absolute value of p. On the right-hand side, we'll have k times t plus constant of integration. We've seen this kind of expression before, so we need to exponentiate both sides. E to the, let me write that actually, before I jump ahead, let me just kind of throw in like some little e's here and here. So that's what we're about to do. E to the natural log of absolute value of p is just going to leave us with the absolute value of p. Here, e to the kt plus c1, e to all of that, can be written as a product, e to the kt, e to the c1. E to the c1 is another number, so I could think of that as c2 e to the kt. We're here. C2 is e to the c1. This is similar to the first example where I've got absolute value of p, and then I've got a positive or non-negative expression on the right-hand side. So C2 is non-negative, it's actually positive. And then we have an exponential function that's positive. But if I were to allow the function p to be 0 or negative, that would be okay if I absorbed the sign into that leading constant. So I'm going to get rid of the absolute values and say p is, how about C3 e to the kt, where the idea is that C3 is like plus or minus C2, or maybe it's 0, depending on the population. And this is the general form. In fact, we usually would write, say, P of t equals C e to the kt. This is our solution. It works if the population is positive 0 or negative. Okay, let me say now finally what I want to about the constants, and that is that throughout the examples today, I tried to keep track of whenever I took a constant of integration and I changed it. So here I started by calling this constant C1, and then I did e to the C1. That's technically a different number, so I called that C2. And then here I was saying it's going to be C2 up to sine, so let me kind of change that into C3. I don't really want to see that subscript if I'm going to say what the general form of the solution to the differential equation is. So then once I've got to the end, I just like to see C here. Honestly, this is not what I do in my personal life. If I am solving this myself, I typically just always call the constant C, even if I've done a little algebra to it. So I would write C, and then I would say, hey, e to the C is just another C, so let's just keep calling that C. That's what I do, and you might see that if you are looking at another resource. So it's not too unusual to play a little bit loose with the expression C and just say, hey, it's a constant. Let's just call it C. In this video, I did want to distinguish between the constants because this is our first time seeing this. So I didn't want to suggest that a number was literally the same if it actually wasn't. Okay, however, it's not too unusual to just see C everywhere that there's kind of an unspecified constant, if you will, while you're solving such a differential equation. Okay, now let me step aside and I'm going to erase this and we'll come back. And I just want to justify this action of separating the variables because there's something a little bit strange about taking dy dx, or in this case dp dt, and splitting apart that expression into two different sides of the equation, right? So is this kind of breaking apart notion the right thing to do? And the answer is going to be yes. But what I will do is show you that if your function satisfies this version, like this separated equation, then it should satisfy the original differential equation. Okay, suppose that we have a separable differential equation. Then the separation of variables method that we've looked at in this video is a technique. And we hope that we can do the anti-differentiation and solve for y ideally so that we can say, hey, this function should be a solution to that differential equation. And that should be is what I want to justify here. So how do we know that when we break things apart and we anti-differentiate, say left-hand side with respect to y, right-hand side with respect to x, that we're actually going to get back a solution to our starting differential equation? So let me suppose that y solves the equation that we get after the separation. Suppose y, which recall is a function of x, satisfies that if you anti-differentiate 1 over g of y with respect to y, you get the antiderivative of f of x dx to constant. Okay, suppose that y satisfies this, because that's what we get when we do separation of variables, is we get a function that makes this true. It will make the original differential equation true, and to see that, let's differentiate both sides of this equation with respect to x. So we'll have, let me start with the right-hand side. I'm going to do d dx of f of x dx. Starting with the right-hand side because this is easier, I'm integrating with respect to x and then differentiating with respect to x. So this is going to be an antiderivative of f of x that I'm going to then differentiate. So by the fundamental theorem of calculus, we know that these are inverse processes. So when I anti-differentiate and then differentiate, we're just going to get f of x. Okay, so that's the derivative of the right-hand side with respect to x. Derivative of the left-hand side with respect to x is a little bit trickier. So let's set up d dx of 1 over g of y dy. Y is a function of x. So we're anti-differentiating y, which is a function of x. All of this we could think of as some expression which is a function of y, which is a function of x. Okay, so I've got composition here on the left-hand side. If I want to differentiate this kind of composition with respect to this innermost variable x, it's actually an application of the chain rule. So relying on this notation h here, let me just write kind of an intermediary step. It would be d h dy dy dx. dy dx is actually what we want to see. That's the left-hand side of our differential equation. dh dy now is like saying differentiate this integral expression with respect to y. So I'm going to anti-differentiate with respect to y, then differentiate with respect to y. I'm actually going to get back 1 over g of y, kind of like we did, or exactly like we did with the right-hand side. So 1 over g of y dy dx. Okay. But if this is equal and we differentiate both sides with respect to x, then their derivatives after differentiation with respect to x should also be equal. So kind of put these two lines together, and we have 1 over g of y dy dx equals f of x, which we can then bring that g of y over to say that dy dx satisfies our original differential equation. So dy dx is f of x times g of y. Okay, so that was just a brief justification that this method is a good method.